whole overall strategy that had been employed is that, okay, we have these BIM surfaces, and what they did was they used these STL surfaces, convert that to two triangles. So this is the real STL version. What I tried to do is in the program that I provided is try to basically combine these two together. Why would we want to put each and every one of these in separates when they're actually the same surfaces? Ours was a bit different, but it basically in essence does the same thing. If you have a point, you basically project it to that surface that is closest to it, and then we check whether the surface is within the boundaries of that surface. Once we check that, then we check whether it's within the distance threshold or not, towards whether a particular surface can be considered as covered or not. And this is basically where we're at, meaning that we've performed this when we perform the ICP and we have a good registration. Now we want to go back and see, okay, now that we know all of these points that are satisfying these, and we have these projections to it, what would be considered a surface that is recognized here? So what they say that they basically take the polygon there of the projected points, and this is just easier because it's the projected, we're comparing it basically with the original there. So you have the covered surface, and then basically we divide it by the original surface. And then if larger than the surface bin, then we're not going to have any problems. Is that there has to be a distinction between the STL coverage and an overall object coverage. So how I'm going to talk to you about it, now you can utilize that in the same way. So you can say, okay, because this is larger than the surface min, and because the coverage inside of the projected points that satisfy the initial constraint is actually larger than the surface min of the covered, in terms of, let's say, 50% of it, or the percentage of coverage there. If that is the case, then we can say that this particular surface is actually covered. Now, an object, just a planar surface is consisting of multiple different types of basically STL triangles. Just that planar surface at least has two if it's just a rectangular planar surface. Now, a column, for instance, that we had, it has 6 surfaces and then 6 planar surfaces that are rectangle. If you have a rectangular, let's say, prism type column, and each of them have 2 triangles that each represent a surface in the STL. So now you have 12 surfaces. How do you then say that that object is the same? So one in inference would be that, okay, we just use the same surface min for the object and say, okay, we take a look at all of the surface cover for each and every one of these STLs. And then afterwards, we basically sum them together and divide it by the overall surface of the BIM and say what that is. And you can perform that as well. And I basically made a distinction personally, but what we're going to be doing later on is that we're going to introduce 2 thresholds, one for each surface and not just the STL, but the actual surface. Then we also do another check for the global, meaning that if a particular object, what percentage of surfaces of a particular object is actually covered. And we have a threshold for that as well. And then we basically say, okay, the surface is covered or not, and then separately if an object is covered or not. Okay. BIM is represented by a particular surface there, okay? So the surface area of that particular polygon that would be considered or should be considered has to be defined here somewhere. And how we define it is basically here where we define ID_BIM. Now, another side of that is which one of the surfaces that point cloud belongs to, right? Because we have a set of surfaces there that come from the attribute here. Basically, when we have that attribute, if you remember, you have a bunch of rows that represent a different surface. So we want to basically, instead of only having to say, okay, what ID of our point cloud is with respect to the X_BIM, which has correspondence between the point cloud and the BIM. We now want to also add the fact that that point cloud also must have a correspondence with a particular surface in that BIM, that STL file, okay? So this is what I'm going to be doing here, is basically I'm going to be using exactly the function that we had here, where we find which surface it is, and that surface is basically the surface that we're using for identifying the disks, right? Because the disk had a particular row and a set of columns that represent the attributes of that. So with that attributes is just the DD of PDI. So a particular point, which is point I here that we have, has an ID that represents that particular surface. Then that particular surface is the DD of PDI. So this is what we are going to be doing. We're going to address and add another type of surface there, or another type of identification there that represents this for every point that we have. Now, we can do it in two ways. We can basically add another, let's say, layer and another column to ID underline BIM, and that is completely fine. And we can basically do it in two columns. But I really don't want to change necessarily how that works. So what I'm going to do is I'm going to basically find correspondence between a particular point I as our ID of surface with the DD of PDI, which is basically the surface that we're taking at every iteration that has a correspondence between the BIM and the actual point cloud. Of ID of BIM, we just have it in another row vector. We call it ID of surface. So we basically do that. So we add an ID underline, let's say, surface. Because if we wanted to actually do the first one, we had to actually change this to N and 2 instead of that for the ID of BIM. So we just copy that as the ID of scan underline surface. That basically means what surface in the STL, which ID of surface that we have correspond to which point. There's a reason why we have to do this, because we have to call that particular ID of all of the points that belong to that surface, and then we have to find what coverage area it has compared to the coverage area of that whole surface. That is going to be found from the function that we just corrected, which is the STL polygon. So instead of ID underline BIM I and 2, we basically do it here as I and 1. And instead of doing it in this way, we just basically change this to find ID of BIM, and we take the other sides of it out. And then we basically now we're going to use the ID of surface and then find the ID of surface that has the find or has the ID of BIM. So we go ID of scan of surface is equal to ID of scan of surface of ID of BIM. That means that whatever is not 0 in or whatever is not 1 in the ID of BIM, that basically we're here, there. So it's ID of scan underline surface of ID underline BIM. And so now, in order to utilize this, the same as what we always do, we basically go and use it as our output. So because we're going to use it, we now have to put it as output, and that's basically how we're going to do it. So now we have 3 outputs instead of 2 outputs in our BIM simulation underline STL underline new. And now that we have multiple outputs, then we're going to have to basically change it in our ICP program as well, because now we're going to be able to call it. So now we're going to have the area, and now let's see how that works. I kind of wanted to show you what that works. So let's go to our ICP underline points STL theme. Let's just copy all of these top parts there. And then basically, instead of that STL part there, we just have to change it to foundation, but let's just copy it first. And of course, first we have to read the sample point cloud. So that is for the column, heritage column that we showed. So it's X underline scan. Have it as sample point cloud. We have that transformation. And how I typically like to do the transformation, one way of doing it very simply, because these are space separated variables, it's always good to basically go through Excel and do it. You can easily do that, but let's just copy it there. If you haven't copied it, you can copy it from the screen. And then let's basically go and find the X underline scan R, and then go and find how we would be able to first translate and rotate it with that transformation. And once we do that, let's go inside and see what happens with respect to ID of our particular surface. So we're basically doing the exact same thing. We say, okay, X underline scan is the X underline scan of 1 to 3 and a set of ones and our original transformation times transformation prime. That's if you have that transformation matrix ready, which we had it and I have provided for you for that particular assignment. And then now let's copy from lines 9 to the rest of it. Once you paste it, and you just change the STL to what we wanted to do. So we wanted to basically use foundation, right? So .stl, close it. And then the distance underline fresh, let's just use, let's say 0.05, just so that it has some bearing. And here we just basically don't even need to copy that because we already have our X underline scan. So here we have our attributes, we have our surfaces, we have all the aspects that we are required. Now what we do is we basically want to go and see how we can perform that particular function. So we basically go and copy that particular function. We now add a ID of scan of surface onto it so that we can see what that represents. So this is just from 1 to 3 because we have 4 columns and we just want the first 3 of them. And the rest is going to be the same. Just press enter. Once you do that, you basically get that ID underline scan underline surface. So what that shows is basically what ID of what surface this particular item belongs to, this particular point belongs to. Once we've done that projection, we now have to find a correspondence between the point and the surface from which it was basically through which it was projected onto. And that's basically what this is. When we say 2, that means that the surface that has ID of 2, that means that if you look at the attributes, which is a 6x4 matrix, and that attributes represents the planar surfaces of each and every one of the surfaces around that foundation. This basically shows that the second, whatever that second is, which one of these 6 surfaces it is, that's what point 2 is belonging to. Okay, so let's go to the PC show, X underline scan, R of ID underline BIM, okay, and 1 to 3, because we want to see what the ID underline BIM is. And now what we do is ID underline scan surface. And the reason why I put it this way, because each and every one of these ID underline scan had 1, 2, 3, 4, 5 is going to be represented by a different color. Because the color coding in the PC show is from 0 to 1, and this has, larger than 1 values, right? We just divide it by the maximum of ID underline scan underline surface, just so that's the number that it gives with respect to that is between 0 and 1, and there's going to be some sort of color associated with that. So it's nothing special in that way. We just add that to give the ability to differentiate between different surfaces by means of the color that it's associated with. So I just divide it by 6 or divide it by maximum of ID underline scan underline surface. And this is just so that the third column has a number between 0 and 1, so that when it visualizes it, MATLAB, it has a color associated with it with respect to point. So you enter it, and this is exactly what we get. And this is what I wanted to show you, is that the ID underline surface gives you the ability for every point that was projected onto a surface to now have an ID associated with it, that all of the points on that particular surface, now these set of point clouds belong to that. And this is where you can color code it and kind of show it so that you can say, okay, this group of points belong to this surface. That group of points belongs to that surface. And these are different from each other. You can segregate them from each other. If you didn't have this ID of surface, you had no option to do that. And the good thing is the way that we had performed it strategically was that we had to actually go through that. So we just use the same calculations, and we just add another variable, which gave us the ID underline surface. So what I want to do is I basically want to copy this whole thing, and we want to introduce a new function. And this function is the object recognition function. So ICP underline point underline STL, we're just going to change it to the object recognition of point to STL or something. Scan, I think it's like object, whatever you want to basically put it. Here I basically do the recognition underline thing. And then in the threshold, we also add that surface min to it. Which is the minimum surface that needs to be covered in order for a particular surface to be considered. And then we, of course, have an object min, or I put it as surface min global, which I'm going to talk about it later as well. So we just put that as the surf underline min. So in the original ICP, this area was not utilized, right? But here is going to be utilized. Here, instead of this, we basically have the ID of our scan underline surface, or surface underline scan, however way you want to do it. It doesn't matter. As long as you call the same function, same variable, you're good. So then once everything is done in the ICP, and in these linear, you can, again, instead of putting all of these, you can basically call the ICP and just have the information that you want from the ICP for the rest of it. You can easily do that as well. I just didn't do that because it's not necessary, but you can definitely do that to utilize that function a bit more, because this way that function would not be utilized in this process. So we first find the unique IDs. The reason why we're doing the unique is that there are surfaces dependent upon the point cloud. Imagine that you have only one side of a particular column, only these two that you're monitoring. So there's not going to be any type of, if you look at it in the other algorithm for the ICP, there's not going to be any other points that would be projected onto the other two surfaces, right? Because of that, and because of the fact that you don't have that ability, there are some surfaces that might not be considered here. And if it is not considered, we need to identify that first. And we only need to perform this strategy on the rest of them. We don't necessarily need to go through each and every one of them. Once we've identified the unique identities, then we can go through it. So The IL, I just put it, it's just one equal, it's not two equals. I mistakenly put that there. We want to find the unique of ID of scan of surface. This means which ID of surfaces are actually have correspondences here in our projected points. Sometimes not all of them have, and this is where you can find that. So which one of them belongs to this first one, which one of them belongs to second, third, fourth, and so on and so forth. And see, some of them might not have correspondences or might have one or two correspondences, which we're going to check later as well. We go and find which point belongs to which surface by finding the correspondence of ID underline surf underline scan underline surf to the IL unique elements as we go forward from the first, second, third, fourth, fifth, and sixth. So we do that. We say 4. Of course, I wanted to first initialize the length of it. Say, let's say PO. Length of IL, meaning how many of them. Coincidentally, this time is actually 6, which is the 6 surfaces. It doesn't really change anything doing these parts here. Sometimes it does change when you don't have any correspondences. So we go for J, I, whatever variable you want to put, 1 to PO. What we want to do is we want to find the ID of the points that basically have the same ID of IL of J. So for that, we basically call it ID of surf. I just put it in those nice brackets. So those fancy brackets that is a cell array. That's what we call it. And the reason why we do it in that way is because if we do it in regular arrays, we have to do it in columns. And sometimes it's nice to call it in each and every one of those rows because that's what that represents, right? But you can also perform it that way. The problem with performing it in columns and matrix is that the ID isn't necessarily the same size. So these cell arrays would be much more beneficial to store these types of information. So go find ID underline scan underline surface equal to IL of J. That means that I go to IL, I go IL of J. For this is if J is 1, it's going to be IL of 1, which is again 1. Like the J represents basically the row. Coincidentally, these two are exactly the same here. So it wouldn't change if I put IL of J or J in this example, but in many other examples, it actually does matter. Once you perform that, now you can see how many. So the first surface, which is the bottom one there that we saw, it has only 1 point that has correspondences there. And the rest of them, some more, some very less, and this only has 58. So we have to now see how much of this is covered by, let's say, how many of these points, and then take it from there. It's J as 0, and then I say J plus 1, and then I do the PC show for the rest of them. So I go PC show, for instance, X underline BIM of our ID BIM of ID underline surf of basically that bracket, that particular bracket, and 1, 2, 3. And then for this, you can put basically a particular number there, just so that we can change it in a randomized color. If you've seen some of my papers and some of the references for the course, you're seeing that it has just different colors for surfaces that belong to the same. We basically do a hold. We perform the same task for J plus 1. Then we enter that. We do hold and another hold just to kind of see how it is. And then take it from there. So this is something that you would get at the end of it. Basically, it's the same thing that we talked about, but this time I just used the projected ones. And this time, not all of them are in the same place that you can't distinguish. Now, each of them are different, right? So if I turn this out, is these points here. If I basically turn that out, it's just 1 point there. We really can't see it because it's 1 point. This one is the top surface. And this is what we want. We want to segment them. And then for every surface, now we get the boundaries. And then afterwards, we want to compare it with the surface, right? So once we have this, let's put all of these in that basically in our nice new function that we've been introducing. And once we're doing that, what I want to do is at this point is I want to find for every iteration that we go in, the surface that is representing to that and its area. And for that, we're going to use basically the same poly underline or the read our STL polygon that we used. We're just using the same function afterwards. So the first part is that we basically, instead of creating a cell array, we basically find the identity. It doesn't matter. Every time it might change. You can keep it or you don't keep it. It doesn't matter. For the sake of my program at this point, it doesn't need to necessarily be the case. So here, really what it is that because we have taken the ID underline BIM of that, here we can actually grab the ID underline BIM here and say ID underline surf of ID underline BIM of ID scan equal to that. So that is what we do here. I just wanted to make it smaller so it's more accessible here. So this is ID underline surf. Really, this is a function of ID underline BIM, right? Because if you remember prior to it, when we were visualizing it, we had to do the ID underline BIM there. And then after, what we do is now we have to find the point boundaries. First, we find the points, and then we find the point boundaries, and then we rotate them, the same thing that we've done, and then we find it within the XY plane, and then we basically use the XY plane, and then we find the area around it, and then we compare it with the surface. When I scan R of ID underline BIM, really, we don't need to do that. We can just work with our X underline BIM, right? Because if we want to do the actual ones, we now have to project it onto the surface again, and we have to find the boundaries. We don't need to do that. We already have our X underline BIM, right? So we go to points underline BIM, and that is equal to X underline BIM of ID underline surf. And column. That means that the rest of the columns of the X underline BIM. So these are the points for a particular surface for the first surface that has correspondence between the point clouds and the BIM, okay? Here I'm giving an explanation that we use the X underline BIM here because it's already projected onto it, and that's what we want. We want to find the projected points, found the boundaries, and then find the area enclosed by that boundary. So for the boundary, there's a function in MATLAB called boundary. Basically utilize from the BIM simulation how we got the rotation. So we just bring it out, and we just copy that rotation down to where we had it there. You could also take it from the read STL file as well that we had. But this time, how we rotate that is that a particular attribute of that, right? Which attributes is it? It's the IL of J, right? Because that's the one that we're going to use, and that's the ID that is corresponding to that particular element. So we're going to use that particular attribute there. So it's going to be the attributes, which is the ID of J, IL of J. Once we do that, what we do with the Rodriguez is that we want to take the attributes of IL of J from 1 to 3. This is the first 3 columns of that. That means the normal of that, because the way that we defined attributes of a planar surface was the first 3 plus the final basically distance, which is a projection distance. And we want to take that into 0, 0, 1, meaning the z-axis. And that would give you that rotation. So once we do that and we find this rotation, then we basically rotate the points underlying BIM by means of this rotation. And now we completely get rid of the the z-axis, and we only use the x and y. And then at this point, we find the boundary of that, the x and y, and then we find the polygon's area. So this is the rotation that takes the attributes under study, the normal of the plane, basically the 3 first columns of that. 2 are 0, 0, 1. This rotation allows us to basically reduce our 3-dimensionality into 2 dimensions in the XY plane of the new coordinate system. So if we multiply the P points underlying BIM by that rotation, that means that we're basically now rotating it such that all of these points are in this XY plane. There's actually no Z deviation in the Z direction. So basically, let's call it points underline BIM underline R. And this here, we basically multiply the points underline BIM by that rotation. And then for the points underline BIM underline R, the first 2 columns of that, we use that to find the boundary and then to find the area of those boundaries. And again, that rotation allows for us to only use the first 2 coordinates for our surface. What we want is here to get the ID. So the index gives the boundary of basically this points underline BIM underline R. And you only want to now utilize it in the first and the second column. That means that the X and the Y. This is important because if you put it as 0, it gives you the overall boundary. If you put it as 1, it gives you the tight boundary. Really, the computation necessary for it to give you the tight boundary is not worth it. So what I do is for this example, I put it as 0. And that would be sufficient enough for this type of situation. And this is what we call a convex hull when you put it as a 0. If it's put it as a 1, which is a tight, it depends. If it's 0.5, I think that's the modified convex hull, if I'm not mistaken. If it's 1, then it's a full, what we call an alpha shape, basically where you find holes and whatnot, and you find the critical value. We also get the area there from that same function, which is our read STL function. And this is basically your points here for the first, and then for the second. And then just here, we use the index of it. That means that now that we found the boundaries of this, we're not going to find each and every one of these points together because that's going to be a significant number of points, especially with point clouds. We're just going to find the area of the surrounding it by means of the boundaries. So we find the ID of this or the index of this here, and we use that for that. And this is basically the area that we're going to get for our basic solution that we're going to compare with the original area, right? So finding the point cloud coverage area for each surface in the BIM. So what that means is this is the surface that is covered by the point clouds that have been recognized as being projected onto that particular surface by means of the dist threshold and by means of the RMSE threshold, right? This needs to be compared to what's to the area on the top, which is the overall area of that surface. It's covered enough locally, it's covered enough with the surface. And then the other check is for the global, which is the object base. Because an object, which is the foundation, can have multiple surfaces to it. And for us, even though for the original people, the surface was important, for us, the object is important. We can represent our BIM as an object. So to check this, we create a percentage variable. So we say, okay, we can do that and say how it is. And we say if, or actually we first have to create what is a percentage variable. So we go percentage of coverage, and I just put a percentage. You can do fraction of coverage, it doesn't matter. You just multiply by 100 or divided by 100, or not multiplied by 100, basically. We just have to be wary of what we would do for the surface underline min criteria that we have. So here, the area of the scan of the J, which is the one that we calculated here, that is the area that is covered by what is projected from the point cloud, has to be divided by the area that you get up there, right, from when you're reading our STL file. For the IL of J, that is the basically ID that we're going to be considering there, right? And times 100 if you're doing it a percentage or not, it doesn't matter. Because I've written it as a percentage, I'm just going to add the 100 there as well, just for safe measure. And actually, I wanted to do that so that we can differentiate between this and the other one, which is for the global one. So I said, if percentage of coverage is smaller or larger, it depends on how you want to do it, but we're going to do with larger or equal than our surface min, then we're going to consider this as a surface that is available. That is a surface that we find to be detected. If the percentage is smaller, then the surface is not detected. And this is where the subjectivity comes into play that I've talked to you about. However, if you want to use a very, very simple algorithm that does these thresholds, this is easy to implement and is good in that sense as well, because it performs, it gives you some consistent results, let's say. So we do the ID covered equal to 1. I'm going to change it and play around with it a bit more, and then if it's not, then the ID covered is not going to be equal to 1 or is going to be equal to 0. And then for every parts, we can basically perform this. So we now have to define an ID of cover by means of a set of zeros. And then if it is covered, then we just change it to 1. If it's not covered, then we just keep it to 0. Have this. We also have to be mindful of the other side of it as well, which is our what type of ID it actually has, or which surface is representing. So that's how I've done it here. I've said, okay, we basically not only do we have it as an ID, but we also have it as a function of the surface that it actually represents, or equal to 1. So we just initialize the ID underline cover, and this is just good practice to do that, to make sure that you have enough points there. So let's just copy what we had there with a surf underline min of, let's say, 50. That means 50%. And let's just copy all of these code that we've written there. And what I would do is you have to delete the ID underline surf, because we use the ID underline surf here as a cell, but here we're just using it as a row vector or a column vector. It doesn't work so well. So then we perform that. So this is basically what you get. That means that the first one and the last one did not have any type of correspondences. That's why it is considered as 0. So in order to create the patch, What we do is we find the basically boundaries of that,